with your physics degree. I'm Crystal Bailey, and I'll be your host for today's broadcast. Thank you all so much for joining us. APS webinars are brought to you as a service of the American Physical Society, connecting you with the expertise of individuals who can offer insight into physics careers, educational programs, and professional development for students, working physicists, and educators. Today's presentation features Dr. Frank Levinson and will be moderated by Dr. Peter Mahuro. Dr. Levinson will be sharing information and insight into his career in venture philanthropy. After Dr. Levinson finishes the presentation, the remainder of the program belongs to you for our question and answer session. Because of the number of people attending this webinar, we are only accepting text questions. So if you would like to ask a question, please type it in the questions box located on the right side of your screen. I also want to remind our listeners you can continue to submit questions through the panel during the entire webinar, and we will answer all of your questions at the end. We will do our best to cover all the questions that you submit, but we want to apologize if we are unable to cover everything. Finally, a link to the recording of today's presentation will be emailed to you after today's event. You will also find a link on the APS page that is corresponding to this webinar. Also, we encourage you to complete a survey upon exiting so that we can continue to improve our ability to provide you with these valuable services. All right, and so with that, let's get started. Moderating the discussion today will be Peter Mahuro, Project Manager for the APS Minority Bridge Program. Peter earned his doctorate in Applied Physics and Energy Policy from the University of Michigan in 2010, and his bachelor's in physics from Hampton University. Peter's professional experience includes entrepreneurship, systems administration, project management, and nonprofit management. At APS, Peter manages the Minority Bridge Program, a program designed to increase representation of minorities among physics PhD recipients by facilitating the transition to graduate school through mentoring, recruiting, and collaboration with participating departments. And with that, I will turn things over to you, Peter.
Well, thank you, Crystal. And today I have the pleasure to introduce Dr. Frank Levinson, who will give a talk on making a difference with your physics degree. Dr. Frank H. Levinson is the co-founder of Phoenix Venture Partners. He has been the managing director of Small World Group, PTE Limited, since 2006. Small World Group is a tech startup company incubator focusing on clean tech, optics, and materials. In 1987, Frank founded Finisar Corporation, a corporation based in California which specializes in optical communications components. Over the past 2 decades, Frank has continued to support his company, including serving as the chairman of the board, chief technical officer, and technical consultant for several years. Frank's other corporate affiliations include Raynet Incorporated, Raychem Corporation, and AT&T Bell Laboratories. Frank holds a Bachelor's of Science degree in Mathematics and Physics from Butler University, and a Master's and PhD in Astronomy from the University of Virginia. And I've had the chance to know Frank from somewhat collaborating on a project that was quite interesting and dear to my heart, and I'm looking forward to this talk because it really shows how you can be an entrepreneur and also make a difference in the world. And so with that, Frank, I will leave it up to you to give your talk.
Okay, thanks, Peter. Let's see here, show my screen. Okay. I hope everybody can see it. Okay. So in preparing for this talk, I tried to sort of go over all the transitions in my career from the time when I received my PhD from Virginia in 1980 until now, and then sort of highlight the ways that you can use a physics degree to do what would essentially be non-physics things, or things that are not directly in the area of physics research and things like that. Let's see here. It is, all right. So the first thing I wanted to point out is there's many ways to make a difference, and as some of you may be young looking at this, I thought to sort of give a rendition of what happens to people that do physics or that interact with ideas in that area. And the example I chose was how the sun works. Because around 1880, astronomers knew, up until that time, that the main hypothesis for the sun's operation had been that it was simply contracting and using the gravitational energy of that huge mass to radiate. But around 1880, they knew that wasn't correct, and they knew it worked by some principle that they weren't sure, whatever. And what they did was they didn't tell any more than tell the physicists this. So when they told it to the physicists, and somewhere between sort of 1890 and the early 1920s, between Einstein and Schrödinger and Heisenberg and others, they worked out a lot of the physics that underpinned, the start of where they thought how the sun would work, and so on. At the end of that time, they told experimentalists, hey, we've got some equations that seem to be holding all this together, and the experimentalists, as you can see in the next slide, the next figure on this slide, they went and built some limited but practical devices. But then they speculated a lot more was possible. Finally, by the 1950s through today, engineers took over and built lots of useful inventions, including, full body scanners and radiation therapy and tracings and all sorts of things. So there's lots of things about this. And in some sense, my career has sort of covered the same timeline. In the late 70s until 1980, I was an astronomer and did both theory and experimental things. In the 1980s, early 1980s, I worked in fiber optics at Bell Labs, but we did more things that were research, some development, but surely not a single thing that I did, made it into any big systems that got deployed. In the late 80s and early 90s, I started a company called Finisar that today is the largest fiber optic component maker in the world and sells lots and lots of components to the world. But essentially, I took the things that I learned in Bell Labs and went and applied them very vigorously. In fact, the company I started was called Finisar, and the reason it was called Finisar was I'd worked at a lot of big companies and never finished anything. So I wanted to finish something and make it practical. And so I shifted and became more practical as we went along. So what I thought I'd start out by doing is give you a little bit of background about who I am and where I am today, and then we'll move into some ideas. So I got a bachelor's, as Pedro told you, from 1971 to 75 at Butler, and I'm really proud of the place. Besides being great at basketball these last couple of years, they have the highest graduation rate of anybody in the NCAA tournament, and it really is a small college academic setting. They have a largest telescope in Indiana still, I think, and it's in the middle of the city for some strange reasons. But I got the keys to it when I was a senior and set it up and took pictures through it, and it's really what got me hooked on astronomy, and then I went and did a PhD at University of Virginia. At the end of my PhD, this is one of these things that maybe gives some of the young people here listening, they weren't sure my PhD was right. Some things in my thesis, there was a little controversy. And so when I applied for jobs in February of my graduating year, I didn't get any. But by May, they were pretty sure it was right, and they were all happy. And one of our professors had retired and gone to Bell Labs and worked. He came back just for a social visit, and so people grabbed him and said, oh, hey, you got to get Frank some interviews at Bell Labs. So I ended up going up to Bell Labs, interviewing everything up there from switch design to integrated circuit design to integrated circuit process design or process engineering, and then fiber optic things. And to my good fortune, I chose fiber optics. It was a very beginning field. I remember one of them asking, what do you know about fiber optics? And I said, I think it's spelled with an F. And they said, okay, you can come. And the reason is there were no degrees in optical communications or anything like that at the time. It was just too new. By 1984, I left Bell Labs, and actually I was with Bellcore at that point, and started a company with some venture capitalists and AMP at the time, who's now part of Tyco, a nicely well-funded startup in fiber optics. And as I like to tell the story, we had a great business plan. It was well done. We went and hired people. We had a nice building. Everything went. We had lots of executives at the company and so on. I was really young, and within about a year, I got fired, and it all didn't work out very well. So then I pulled back and went to California, out in Silicon Valley, and joined a company called Raychem, which was the founder was still there, a guy named Paul Cook, and a very sales-centric company, but also researchy and clever. And I learned a lot from them. And they spun out a division called RayNet into a company that was trying to do fiber to the home, which now is taking off, but it was too early. And I was with them 3 years, and then in February of '88, end of '87, I founded Finisar Corporation. And for 2 or 3 years, we did contract engineering. We had no written down business plan ever in the company. By the end of the second year, we began designing products. So I like to say, we spent 2 or 3 years designing products for other people. Then we spent 2 or 3 years designing bad products, and then finally we got it right. And so Finisar is a company that today builds transceivers. These are devices that take electrical signals and convert them into optical signals, and then optical signals back into electric. The devices are typically about the size of your finger. They can sell anywhere from below $20 to above $1,000, and they operate at bit rates anywhere from 1 gigabit per second to more than 40 gigabits per second. And in 2006, I left full-time with Finisar, stayed on the board for another couple of years, but I founded Small World Group, which is a company that I did to try to, and a group of companies really, trying to give back some of the things I'd learned, as well as trying to give back and start companies under the same principles that I'd used there. What happened here? Okay, so there's a little bit about me. Small World Group Ventures invests in companies. It's a venture capital firm. It's here in the U.S., and we focus on clean tech, optics, communications, and materials. Our funding, as you can see here, is below $1 million, and we've invested in companies in Indiana, California, Pennsylvania, Minnesota, and soon in the UK. We almost always co-invest with others, and our companies try to achieve revenue quickly. Small World Group Incubator operates a startup incubator in partnership with the Singapore government. And again, we focus on the same things: clean tech, optics, communications, and materials. Our quantum of funding is 600,000 Sing, and the team size is 4 to 6 people, and that funding typically lasts 12 to 18 months. Again, we try to form companies that have revenue quickly. And lastly, Small World Group Social Ventures, or Small World Group Institute, makes philanthropic investments into scalable, sustainable social ideas and ventures. And currently we have projects that we're doing in biodiversity, in water, and in forests. Again, our quantum of funding, if you will, in this case is anywhere from a few $1,000s to up towards $1 million. And but like the ventures and incubator, we try to do our philanthropic things in ways where they must have a plan. The funding will come in phases, and we try to make sure that we really have milestones and we have ways of reviewing the progress and things like that. So again, in the question side, we can talk about all these things. Okay, so the question that I try to understand as I was prepping for this thing is, what questions would you have out there? And the first question I hope somebody would ask is, am I right for this, or are you right for this? So here's some key questions. The first thing is, where have you worked? I don't know, if you've mainly done teaching and mainly done and had an academic career, and that's what you seek to still do, I think that's great, and staying in physics may really be the right thing for you. But if you've worked at these same things like this at McDonald's, Old Navy, Home Depot, Walmart, and if you like to do things like invent, tinker, maybe design or build your own home or a deck off your home, if you like to code software, if you like to repair your own car, then that, in combination with a physics degree, either undergraduate or postgraduate, can be a very powerful combination. Because what happens in businesses is ultimately you have to like working in teams, working with people that are called customers, and doing things that have a practical side to them. But these practical businesses really need people that have broad understanding in the way that the fundamental things work. And what I think physicists are really great at least what I always have used for my degree, was looking at an idea and going, does that make sense? And on the back of an envelope, we summarize the basic principles involved in this thing and see if we think that there's really a breakthrough. Is there something that we can use here and move forward? So to me, the fact that I've always kidded people as I give talks, well, I just have a PhD in astronomy. They look at me like, oh my goodness, what does he know about fiber optics or clean tech? But to me, I've always had confidence that by knowing physics, I know the fundamentals of everything. And the fact that then I like customers and like hearing what they need, I can pull from my bag of tricks and the things I've learned over the years to try to meet those needs. The next key question is can you sell yourself? These are silly pictures off the web on the left and right side of the title here, but that's part of it. As a physics degree holder, you're going to have to sell yourself. Find ways to make jokes about it, but also let them know, hey, physics is something that's powerful, and it can be a powerful part of any team I join. So I think that's really important. Again, I tend to go through these slides and have pictures on them that are there, but not really go through them in detail. I almost never read the text on the slides. So the slides work both, as a visual thing to help us, talk and for me to talk, but also for you to look through later if you wish. So don't be concerned that I don't read everything on the slide. That's actually something you shouldn't do. So I think we're doing that fine. And finally, you really need to want to work on other people's problems. If you are the kind of person that sees the elegance of physics and wants to choose exactly the problem you want to work on, and then go after that, that may be something that really is a fundamental part of what you do. On the other hand, if you can listen to someone who has a need and not just build what they want, but in fact build something better than they want, build something that delights them. The world thought they wanted tablet computers, and there's all sorts of tablet computer providers for the last 10 years, from Microsoft to Dell to everybody, and HP and so on. But nobody succeeded until somebody designed something that wasn't just what people wanted, it was what they needed, it was what delighted them, and the iPad's clearly an example of that. So the real art of working in a company is to try to do that. Again, it's understanding that you'll still bring creativity and definition and everything to a problem, but ultimately you're going to work on a problem that's specified by others. Even if you start the company yourself and it's your company and you own all the shares and so on, that company typically won't go very far if you're not working on problems that are there, more specified by your customers than by you. That was the problem with the first company and why I got fired. So in general, your work will be also a part of a larger puzzle. It won't just be a single solution that you give the world, and you'll be working in groups where collaboration is really an art that's not the same as when you're in, especially undergraduate, where collaborating on a test would certainly be against the rules and be called cheating. Here, collaboration is really important. And finally, one of the things that I've tried to break people of over the years as I became a manager was many people that have worked for me as they came out of school, they were glad when I gave them a problem. They liked working on some problem for somebody else, but their first thing was, I asked them, well, how long do you think this will take? And they'll say, well, 3 months, And I'd say, okay. And they'd say, okay, then I'll come and see you in 3 months, and I'll show you what I've got. And I said, no, you won't come see me in 3 months. You'll try to come and see me in a couple days with your plan. And then a week after that, every week after that, we're going to meet and talk about how you're doing on your plan. Because We want to, I don't want a surprise in 3 months that it didn't work, or it's not what we thought, or it's better than we thought, but we didn't know how to use it, or use all the features you put in. So it's important to not try to think that you can retreat to a cave and work in isolation. You've got to like having deadlines, reviews, partners, schedules, and all those things as well. And that's just something that's a part of the business world. Okay, challenges and solutions. And here I had a little bit of fun with some of this, so bear with me. So first of all, the question for you is, if you're going to leave physics, do you want to work for GE or GM, the big companies, or do you want to work for an SME, SME? Those stand for small and medium enterprises. And highly structured big companies with large existing markets, they're often not really driven to innovate as much as smaller companies. And the reason is, if you've got an existing business in turbine engines or wind turbines for that matter, those companies are pretty much talking to their customers all the time. They know what their customers want next, and so they can do evolutionary products. They've already got a customer base, and that customer base will help them do very successful evolution of things that they already have. Little companies on the same scale, for the same reasons, can't compete with big companies that have these existing bases unless they innovate and provide some dislocation, some revolutionary product that causes the people served by the big companies, the big guys, the MNCs or multinational corporations, and unless they can dislodge that belief that, hey, evolution alone will get us where we need to go. So that's your first question, is do you want to work for somebody big or somebody small? By the way, both of those things can be a little bit disconcerting. You think, well, I'll work for a big company and be able to stay with them your whole life. If you did that and started in fiber optics in 1980 or even 1988, let's say, and someone asked you, how's that going to go? You're with you'd say, well, I'm with, AT&T Bell Labs. They're the leaders in fiber optics from the beginning. They're the largest fiber optics, groups in the world today. You'd expect that to be the same in 20 years, but you'd be wrong. The groups that, the group that's the largest today is the company that was started by myself in 1980, literally just by myself and with a couple of partners, and today it's the largest company. We sell by far the most transceivers and the most devices in the world, and we actually that company sells between 10 and 100 megabits per second of bandwidth per month per person on Earth. So as a scale, it's an enterprise that really has a global reach already. So another question here is, what happened here? So the question is, would you even like to start a company? And so that, let me tell you a little bit about how that goes. If you do, I don't know how this slide is a little bit out of place here. Life at the SME end of things. Let's do that one. I'm sorry. So what do we do when we try to work with these small companies? Because that's the thing I know about more than big companies, as you can tell. First of all, today in the area of clean tech especially, and Peter knows this, is we really try to form and work with international teams. We like diversity. We like reaching out to things. The thing about clean tech is you try to make solar cells and solar panels, for example, work in the U.S. You have to be competitive against oil and gas and even other things, that are even more renewable than that. And the challenge with that is we're such a developed country that we have a very highly developed infrastructure, and so to compete there is tough. On the other hand, if you want to charge a cell phone in the deep third world, the information we have shows that you typically spend between 100 and 1,000 times as much as we do in the United States per kilowatt or per watt hour, if you will. So in fact, if solar cells miss by being competitive by a factor of 2 or 3 in the U.S. and Europe, they're a factor of 200, very competitive compared to the price that people are paying for that same watt of energy in potentially Africa and some parts. So to work in these sometimes international areas is an interesting thing. Again, one of the things that people have found is that you're open for dislocations. In the West, we still mainly make phone calls using wired telephony. We pick up a phone and we make that call. historically, we're talking over wires. If you make a call in India, you're almost always talking over wireless. They skipped wiring the country out to the individuals. There was no reason. They could put cell towers with enough density, and then everybody could talk with that. And so they never ended up putting the wires all the way to the end. That's just not what they did. They leapfrogged the Western deployment of technology to the more modern. And we think those same things could be possible with clean tech. One of the next things we do is I think this is really important as you look at ideas and things that you might want to do with your career on the very innovative side these are pictures of how people drove cars right around the time that cars were invented. And it turns out, I love these, because nobody knew how to drive the car. And I couldn't find a picture of it, but there were cars that were driven by reins, like a horse. There were cars that were driven by a tiller, like in a boat. There were cars that were driven by bicycle handlebars, like the one on the right, at the upper right picture with the fellows with their hats. There were others that were driven by levers on both sides, kind of like cranes or cats were. And there were some driven by silly little steering wheels, like you see on the bottom left. And eventually they settled on steering wheels like on a ship. But nobody originally thought that taking an idea of how large ships were used to turn and applying it to a car. They chose examples from bicycles and horses and other things that were already land-based transportation initially. So in general, when you try to architect something today that's new and inventive, as you will, in a small company, you may have to think about, you have to just re-architect it completely. Again, Jobs didn't try to make the tablet computers that have been selling for the last 10 years just a little bit better and make them an Apple brand. They had to reinvent even how the touchscreen worked and all that stuff so that it would be really successful. And so I think that's part of it. So by re-architect, think of the actual, think of this example of the cars, and that nobody knew how to drive them. Finally, we need to question some fundamental assumptions, and I couldn't resist this set of pictures here. Someone once told me in a meeting, and very serious, these were serious environmentalists, that they weren't sure that toilet paper was sustainable. All of a sudden, I got really concerned. I wasn't sure exactly how we would get that job done. Then I found this wedding dress made of toilet paper, so I thought I'd show it to you. But the point is, there are going to be things that we're doing and we take for granted today that aren't going to be sustainable, that aren't going to be practiced in 20 years. And what are those? And to the extent we can identify them, find them, use our knowledge of physics to go seek a part of physics where we think that we could apply it and change that and lay a new foundation in place. Again, that was done with the wired telephony in India, and there's going to be lots of places to go do that in the future, especially in the areas of clean tech, I think. Okay, a little bit about us as an incubator. So what I do is I start small companies, and I just thought I'd show you one slide of the kinds of things we're working on just so that you can see it. In the far right column, I hope you can see my mouse, I can, the companies we've invested in, one does literally energy monitoring. They can go into a building or a home even, I suppose, and deploy a system that they just clamp onto the existing wiring and gas and water infrastructures, and then it puts it all out in the cloud. All the data collects moment by moment, and then you can access it by your computer, through a web browser, by an iPad or an iPhone, or another type of cell phone, and you can see. Eventually, you should be able to even turn things on and off. So it's a way to, and it's been shown that people have done this already. Typically, end up saving about 30% of the energy the first year they have this system, and then they use it going forward after that, after they achieve the initial savings and realize how they could do better. They then tend to use it for finding problems that crop up over time. I was in a house today where someone was saying, yeah, we had a bad transformer out to the house, and our electric, as soon as we found it, our bill went down by 2/3. Another night I was actually traveling, but I called back to my home and to the people there, and I said, hey, what's going on? The toilets, we're using, a staggering amount of water in the last 2 hours, more than we have in the last week. It turned out a toilet was leaking, and they just had to jiggle the handle, but it was losing 600 gallons an hour, and we typically use about, 60 or 70 gallons a day. So, so that's what that one does. Next one is a building energy modeling. It uses a Department of Energy computer model, but it's based on physical principles. Another one is a wild sports gadget that has accelerometers that they put on various sports things and do some crazy measurements and then some physics modeling, and that's cute. Another one is water use monitoring that uses some interesting physics principles in how they detect it and so on. And the last one is a manufacturing group for clean tech. We're working on a power device for the deep third world. That's a sort of a personal power device. It's a Swiss Army knife of power. And we're working on an energy storage device that's very different. Again, as we move back in here, a couple of these are one's a water storage and use system that tries to keep things clean from collection. One is a approved internal combustion engine. That's highly risky, but interesting. A different set of principles again, but still following the same laws of physics. So that's why we like it. Biomachines is an attempt to use to make some new types of harvesting and equipment for the deep third world in places that they do farming, but they use very primitive means today, and we think there's ways to actually do farming more sustainable if we have the right equipment. So you get the idea, and we can talk about this in the questions and answer period if you want. So in summary, there's plenty of room for physics and creativity outside of the pure science area. And I think one interesting place to look for all of us is to look carefully at the bottom of the pyramid. To do that, though, you've got to erase old ways from your thinking, to re-envision how things can work. And both small and large companies can make contributions, but the really interesting area, I think, can be in the small company side. And with that, I'm going to turn this whole thing back over to Peter and Crystal, and we'll take questions. And again, I didn't specifically talk about the philanthropic side of this, but actually some in that table are projects that are not for profit and some are for profit. So we can move in around any of these subjects as you guys ask questions. Okay.
Well,
all right.
Thank you, Frank. That was quite enlightening, and we have such exciting questions. I'm looking forward to going back and forth with you, and I'd like to just encourage the audience that keep sending your questions in, and in fact, Frank has even offered to stay a little bit longer after the hour if there are many questions, and so don't feel like we're out of time because we're interested in hearing more what you have to say. So one of the questions that just seems to capture people's attention is how do you define clean tech? You're speaking of clean tech, but exactly how do you define that?
Wow, that's a tough question. So typically, clean tech is technology that involves renewable energy, sustainability, energy efficiency, water in both its use and reuse and recycling and collection, trash, and all sorts of things that end up with biology as well. An example I've heard of is that historically, for example, cocoa has been harvested. Cocoa for us is a seed, and they do it. They treat it in certain ways and then grind it up, and that's what we get for cacao or chocolate. But it's actually the seed that sits in the middle of a fruit, not as big as watermelon, but kind of like watermelons, I guess. It's much smaller, and it's harvested. It's taken out of the cocoa plantation and then processed in some other place. And as you do that, you end up taking the seeds out and being able to do it all what seems very efficiently. But as you do that, the actual fruit is what you remove. It's the stuff you end up throwing away out of that factory. The seeds are what you keep. And so, but the plant typically works really hard to put a lot of what it wants into those fruit. And so by taking the fruit out of the plantation, you're removing from the soil a lot of really important nutrients. So to the extent that you could find a way, for example, to process cacao right in the plantation and return things to the soil that were not part of what you're using. I mean, if you only want the seeds, leave all the rest. It turns out you can do things like that better. And so I think there's lots of opportunities in the biology area as well. So it's re-questioning how we do things to make the world more sustainable. We're at the point right now where almost in every dimension you look, there's strong questions about whether we can go on doing things the way we have. Some really good books in this area, Peter, for all of you. One is Sustainable Energy Without the Hot Air. It's a wonderfully written book in 2 parts that talks about the UK's energy budget, and it goes through, first of all the uses of energy inside the UK, and then all the sources of energy. And the second half of the book, it goes through in detail the physics of the questions and assumptions that they had in the book. The first half, all you need is a 7th grade algebra, a class that you pass to get through. The second half of the book, you need an undergraduate degree potentially in physics. So he's worked hard to make it very, very approachable. Another one is called When Rivers Run Dry. It gives a very scary picture about how the world is evolving and how we're going to run out of water in many, many places within the next 10 to 20 years where water today seems plentiful. So I'd say clean tech is something that all of us need to learn a lot about. Go ahead.
Well, so just to somewhat tie into that, another question that we've received is a question of, so is there anything that you're working on relevant to hybrid electric technology? This morning on NPR was folks talking about how they have a hard time plugging in their hybrid cars because they live in an apartment. And so in some of the technologies and some of the things that you've thought about, I know you've talked about re-architecturizing, if that's a word I could use, things. Is there anything that leans towards something like that?
Well, there is. I mean, one of the big areas that's extremely interesting in the world is, and again, it really comes out clearly in this Sustainable Energy Without the Hot Air. There's many other books to recommend, but what's so nice about that one is it highlights it just it highlights how hard it's going to be to really make close the energy gap if you're not going to burn carbon. So in essence, in that one, what's a big deal is even if you get enough renewable energy, in the UK it could come from wind, it could come from wave and tide and so on. Even if you could get enough, which is highly questionable, the problem is some days the wind doesn't blow and some days the tides aren't so great. And so the challenge is how do you store energy? Let's assume you put enough things out, enough wind turbines or whatever, so that some days you get too much. Well, the question is how are you going to store it for the times when you don't have enough? And so that storage problem is, for example, one really big issue. And of course, it's at the basis of a hybrid car. What the hybrid cars do is essentially when they break the car, they save that energy and then they give it back to you as soon as you try to accelerate again. And that small change, it turns out, has a big impact on mileage. Actually, they do 2 things. Just to tell you, because I own a couple of Priuses. The second thing they do is they let you put in a much smaller gasoline engine. And by using the electric motor, they give the car back a little bit of peppiness. So what looks like a 90 horsepower car really isn't when you allow both the electric and gas motors to work at the same time. It goes back up, and so it lets the car have a little bit more lively response. But yet, as you're driving around normally and just sustaining that speed, the gasoline motor is sufficient to do that. And so it's really a trick. It's both those things. It lets you have a smaller motor, and that drives efficiency, and it then uses also the braking to help you. So this hybrid thing is, I think we have to figure out how we're going to do some of those things. Again, apartment buildings are just going to have to be architected where people can plug in downstairs if you've got a parking space. Today they don't want to do that because you don't own that outlet. You own the outlets up in your apartment, and that you have a meter for those, but they've not dropped one down for you down there. So it's a challenge. And if you do plug in your all-electric vehicle, it's likely to be the biggest use of electricity you have in that apartment. So they don't want you to be billing it to the apartment owner. They want you to. So there's lots of issues like that that's going to happen in society where we've got to consider it. And yes, we are working on energy storage. One of the things if you look back, I don't know if you guys can still see this screen. But we're clearly working on an energy storage device that I think is very interesting and very different approach, very different than what's conceived out there today.
Well, we'll look forward to hearing more about it in the future. Just to kind of take a little bit of a twist to things and just switch the gears a little bit. One of the questions we have from the audience is how do you navigate the cultural differences between academia, especially as a graduate student, and the corporate world, especially the fact that you went from a bachelor's degree straight into graduate school, and after graduate school you went on to the corporate world. And how do you navigate that? Because sometimes, and from my own experience, you get caught up in this academic feel of all you know is school. But how did you engage into being able to navigate through all that?
Well, I think part of it is still having that social side to yourself. Growing up, I worked in clothing businesses, and my children worked in clothing and food services, all three of them. So I think it's partially that. It's finding ways to get access to customers, because what's really unique about a customer, someone that uses an idea that you have at the moment, let's just call it that even instead of a product, but someone that uses an idea, it is in talking with them, you'll get a much clearer view of their needs than if what happens is a salesperson talks to the customer, then the salesperson comes back and talks to the head of sales, and then the head of sales talks to your boss, and then your boss talks to you. That doesn't work as well. And honestly, that used to happen a lot in Bell Labs, but I found ways to circumvent that. I would try to travel a little bit if they'd let me, and I tried to go find who were my customers, who were using my ideas, and talk to them face to face. What do you like about this thing? What don't you like? Wow, you want it to be 10 times smaller? Oh, that's really hard. Here, let me show you how we build it. Does it really matter? And so on. So it's that, I think that the business world, that bridge is the way you cross it is by finding ways to get directly in touch with the people that are going to be the users of your products or ideas.
Well, and just to somewhat tie into that, another question we had was, so some of the places you originally worked, for example, at Bell Labs, used to have a very large R&D initiative and a really good budget for that. But today it seems like there aren't as many big players that bridge the spectrum between academia and industry. So what are your thoughts on that, on this kind of landscape, and how would someone navigate this if they're interested in kind of going into somewhat the same path that you took in something like Bell Labs, for example?
Well, again, if you're in a bigger company like Bell Labs or IBM, and those are terrific places. And the place to start may be in one of the research groups if you can get in. Those are the hardest jobs to get. But if you go into one of their more practical groups that have real customers, I think, again, get in touch with their customers as quickly as you can. Try to take out any intermediaries. But how do you get in? One thing to do is to study what they're doing. Go look at their products before you interview. The nice thing about the web is, compared to when I was doing it and so on, the web shows you all that. You can search for people by name, and you can look at what they say they're doing on LinkedIn. Almost everyone in this world has their resume today on LinkedIn in one form or another. And so you can find out who the people are that you're going to be interviewing with before you go for the job. You can then do a little poking around the web about what kinds of research topics they've had or products that they've worked on. Go look at the product data sheets and see how the product performs. Go see who some of the competitors are. And again, all those are things that you can do today because of the web. And so the web gives you, as a person trying to get a job, a really set of powerful tools to interface with those opportunities compared to what it was 20, 30, 40 years ago. You'd go in and because those places were often even secretive, you had no idea what they were doing. And today, you can find the data sheets and the product specs and even white papers and all sorts of things about what people are working on and what they're currently doing and what they're selling and what even maybe are the problems if you poke around enough.
Oh, that's
go in prepared. Go in very prepared. That's the more prepared. And don't go in prejudiced like you know everything, but just go in so that you're ready to ask them questions. Your ability to ask them good questions can always be something that piques their interest, I think.
Well, that's great. And just to continue on, and we have such interesting questions and careers that I'm glad that, and I really encourage the audience to continue asking these questions. One of the other questions somewhat ties into what we've just been talking about is, do you think it's reasonable to go straight into developing a startup? Let's say if I had a great idea immediately after receiving my physics PhD, or is it generally more valuable to gain some broad experience before considering this option? How would you navigate if you were to go back and navigate that question?
I would say if you're going to go by yourself, then I think it's better to wait. I think it's better to get some experience with a bigger company. If you're going to go in with a partner who may have business experience, probably some sales experience, comfortable with even accounting and other things, like that, wow, don't hesitate to go early, because that partner can help you with the things that you won't have encountered if you go in early in your career. The nice thing about going in early is you're very energetic, right? You can wake up early, stay up late, all those things that an old gray-haired guy like myself doesn't do quite as well as I might have used to. So I'd say, go early if you can find a good team to go with. That, we miss it. When you see Mark Zuckerberg and Steve Jobs, you miss really how ventures work. They're not about one guy. Almost always they're about teams. It's Hewlett and Packard. Finisar my partner was a guy named Jerry Rawls, indispensable. Certainly probably even more indispensable than me, even though certainly he didn't have any patents and I had a bunch of them. I felt he was always more indispensable to the business than I was, and I was terribly glad for him to be my partner. So I'd say, the people you partner with are a very important part of that question you asked, Peter.
And what would be your recommendation for someone who is interested in a PhD but is say a junior in college and they're thinking, I want to go for my PhD? Would you recommend maybe taking a break in between, or just going directly and getting the PhD, or what would you suggest?
That's a really good question, and I'm not confident I know the answer, but I'll tell you what I think it is, and that is don't wait. I think to the extent that you wait, your physics, anything you do in physics atrophies or it gets old, and the only way to stay on the cutting edge is just a push to stay on the cutting edge and stay there. If you're going to get your PhD, if you think you're inspired to go do that, do it. I loved getting it, my PhD. I wasn't the best PhD student, If you ask University of Virginia, they may be nice today because I've done a little philanthropy with them, but I'm telling you the truth. I wasn't that great, but I loved it. I just loved it, and I love the idea of seeing things that I thought I saw for the first time before anybody else, so I loved it, and it's something I would never trade to not do. So I would say if you have that inspiration, go do it. The things you get from it are priceless, and you're not likely to do it if you wait. So I'd say don't wait.
All right. Well, that's really wonderful. Now, I just kind of want to go into the philanthropy, and we've had quite a few questions in that
Sure.
area. People are somewhat interested in hearing more about. So one of the questions is as a VC, do you find it that you're actually making a difference in society? It seems like there's a lot more, I guess, what you would call angel investments over VC firms that would actually be making much investments in for example, in developing worlds. And so, what would be your take on this?
Well, let me talk about a couple projects that I've done that are or at least one that's purely philanthropic. Okay.
Okay.
But it still is a venture, and I love it. About 11 years ago, I started working with the Smithsonian in Washington with a group called the Smithsonian Tropical Research Institute. The Smithsonian has two really big, relatively famous science groups. This group probably knows the Smithsonian Astrophysical Observatory, which is located at Harvard, and in partnership with Harvard, I think. And clearly, they're very important in high-energy astrophysics. They're the ones that have done most of the X-ray satellites and things like that. The other one is the Smithsonian Tropical Research Institute, which has been located, headquartered basically in Panama for a long time, 40, 50, 60 years anyway, probably more like 100. They are in Panama, but they have a global reach. And in 1980, they started an effort to census tropical forests. So they on this island in the Panama Canal, they set aside a 50-hectare region. A hectare is 100 by 100 meters, so you can sort of picture how big it is. It's 125 acres. And they tagged and identified and measured the diameter of every tree down to 1 centimeter. And there was, I think, 300,000 trees. There's more species in those 50 hectares by I think 3 or 4 times than all of North America. Biodiversity increases as you drive to the equator. You just have more different, just different genomes down there. And if you go drop all the way down to the equator in Brazil from Panama, which is about 10 or 11 degrees or something like that, you get another factor of 2 or 3, I think. So it's one of these things that's remarkable. But they wanted to know, is the forest dynamics changing? Does it change with weather? Does it change with, they didn't think about global warming and climate change at the time, but clearly that's a big deal today. And so they began doing it, and they began censusing this every 5 years. 10 years later, I think there were 4 or 5 of these plots. 20 years later, there was 12 or 14 of the plots. That's when I got involved and began funding this research through my philanthropy. And so for the first couple of years, we funded it, and it's a group called the Center for Tropical Forest Sciences. It's inside STRI, the Smithsonian Tropical Research Institute. And in 2005, the director then of the Smithsonian, STRI, and the head of CTFS were all in Singapore with me over there. And I asked them, I said, yeah, you've been doing this thing now for 25 years. What are you going to do for the next 25? And they said, oh, we're going to do more and do it better. And I said, we're going to do it a lot better. And I funded a study where they studied how to do what they were going to do better. And we got 6 groups that looked at 6 areas that we thought we could add. And of course, they wanted to add more sites, so that wasn't even one of them. But we studied carbon sequestration. We studied doing DNA barcoding. We studied doing paleontology. We did bioinformatics. We wanted to make sure that the whole database that they had collected and that we're going to collect in the future became sort of open source so everybody could use it around the world. So if you had a forest problem in the tropics in Malaysia, you could then go back and say, well, how does that relate to what they've already learned in Brazil or in Panama, and do that. Same thing with Africa. We did traits, and we did other animal species, and we've added below the ground stuff as well. So each of those groups were study groups of 5 to 10 people, and then we began doing it. Today there's 40 sites around the world, just 10 years later, and we've started adding the temperate zones as well. There was a book published called Collapse by Jared Diamond, and it shows that every large societal collapse has been preceded by collapse of forests. And so I thought that's particularly interesting now that we're looking at climate change on a global scale. It's a fascinating read if you go do that. And the project, which over the first 25 years had sort of been funded at a $200,000 or $300,000 a year at most rate, today has investments by HSBC Bank, Mellon Foundation, Harvard, I think Yale, the Smithsonian, myself, but all that adds up to probably $50 million. So it's millions of dollars a year now that are being spent on this, and it's become a big project in the last 5 years, and it's changed its name from the Center for Tropical Forest Sciences to SIGO for Smithsonian Institution Global Earth Observatories, and so they really are trying to create a set of global Earth observatories for us to start monitoring biodiversity on a very systematic and deeply scientific basis with a lot of different thrusts to it. But again, my physics background, I'm hammering on this one, I guess, because of the audience, but it really helped me figure out how to do that, to pull that together and say, well, Can we adopt different ways of doing the measurement? Can we adopt different ways of doing sampling, and can we adopt different ways of recording data and so on? So I think all that's been really interesting, and it was done in a very venture way, but it was venture philanthropy, and that the money was not done for a for-profit motive. But nevertheless, once we got the project organized, and that's what every venture is, right? It's taking a very chaotic problem where nobody has any confidence of success and flipping it back to something that can be done, and can be seen as having less risk. So venture philanthropy is where you take a problem and you take the risk out of it, so that the big funders of the world, the Bill Gateses and the Ford Foundations and the Mellons and HSBC banks, can say, wow, this is something I want to get involved in. They've got the kind of big money you can go do. So, okay? So there's, that's an answer, I hope, to the question of how you do
well,
that.
And just to somewhat, I think it somewhat really ties into that, and just really
you know about this, Peter, so.
We have one or two more questions, and I just wanted to, if the audience, one of the questions, actually a few were kind of alluding to the question of how do you really create profit in a third world country, especially if you look at this, the 4 to 5 billion who are making less than $2 a day. How does some of your technology, and as a physicist, how do you think through being able to create ideas and technologies that could actually generate profit for the quote-unquote bottom of the pyramid, if I may refer to that statement? And how would you be able to actually reach to them and make a difference in their lives while still creating profit? And I know that's a really big question, so.
Well, I think you've got to try to look and say, if they had something that they spent 10 cents a day on, or 10 cents a day, how about even 3 cents a day? Is there something that if they spent 3 cents a day on, they could profitably own? And the answer, we've come back to that question, that's $1 a month, is in many questions, in many things, yes. If you can invest $1 a month for 5 years, we can get you something that you can own profitably and probably make $2 a day, or $2 a month by owning. So you spend $1 and you make $2. You have to find some way to get the financing for that in place. But no, we're absolutely convinced that the bottom of the pyramid has lots of opportunities. And the more we look at it, the more convinced we become. So we think it's you've got to be careful. You've got to be very careful. But Finisar had to be careful with how it made fiber optic modules. I mean, what really happened and why Finisar today is the largest maker of these things instead of Bell Labs or these other guys is we took on the datacom market, which is incredibly price sensitive. Compared to telecom, which was Bell Labs' home turf, it's the deep third world. But it turns out that if you're going to build 20 or 30, or 10 or 20 million modules a year, you build your own ICs. If you're going to build a couple 100,000, you don't. Well, a transimpedance amplifier for a part, even at 10 gigabits, might be $1 or $2 if you buy it. On the other hand, if you make your own IC, it's 12 cents. And if you do it right, the receiver optical subassembly you build with the other guy's transimpedance amp, which you bought for $1, probably cost you $3 to $4. If you use the one we made for 12 cents, it actually might cost you $1.50. So there's things that you can do to engineer value out of the chain, but you have to have the scale. And what the deep third world does give you, if you can find a solution, is it gives you 1 billion customers. not the high-end where there's lots of competition and a lot more marketing and advertising driven. These are opportunities based. These are value-based propositions in the deep third world. So if you can find one, the chances for it to be profitable, I think, can be still very good.
So just to somewhat wrap up, one of the questions that actually quite a few people have asked is there a way people can apply for monies that Small Walls Group Investments has, or is there a way to contact you if someone needed to talk to you, or is there any last piece of advice you can give in wanting to get into this kind of area?
Sure. I should have said that my last slide shows the Small World Group team. It's a couple guys in their late 50s. It's one of us is Asian from Singapore, Chet Bing. Dean is Caltech and Stanford and is 36 and a terminal cancer survivor. Chris is in his mid-40s. The way to contact us is all of our emails are there, but you can go to the Small World Group website, just www.smallworldgroup.com, and you can find us. The emails are there, and we're happy to hear about people that have ideas. If you want to move to Singapore and work in one of our companies or join a team over there, we can help even talk to you about that. And Peter knows the story of that. He's come over and stayed in my apartment even. So we're always looking for guys that want to work on problems and that have ideas. And I got to tell you, the venture capital process is not a lean and mean one, but it is a lean one. We say no a lot. And that's just part of what we do. But we try when we say no to at least tell you why. And that gives you a chance to go work on it and bring it back again. And so I'd say, sure. And if you're someone that wants to get your feet wet, joining a team that we help form up, because we always try to have balanced teams. We invest more in teams than ideas. I can tell you that. The number one criteria for whether we'll fund or not is the strength of the team over the strength of the idea. We want strong ideas too, but most important to us is a strong team, and we'd love to have some guys in physics consider joining some of our projects. So please get in touch with us.
Well, that's wonderful. And just to wrap it all up, there's a question that's been, of course, eating me up and many other people, I'm sure, is in your first slide with the crazy hair and everything, could you explain a little bit about that? I think
Let's see if we can go back there.
It made everyone wonder. So. Well,
I wanted to show you that, it turns out I actually look more like the crazy hair guy than the guy in the picture. But if you look on the web, all you get is the other one. So I just wanted to be realistic about this. This is a picture of me in my house. It makes me look like a scientist. so I threw both of them in. But I'm the same guy in both pictures, I guess.
Well, thank you so much, and Frank, we really appreciate your time today, and just this moment to talk with us and present your brief life history and all the great things that you're doing. And like you said, if anyone has questions, they can always get a hold of you at any point. And at this point, I am going to turn it over to Crystal, who will wrap us up.
Okay.
All right. Yeah, thanks, Peter, and thank you, Frank, for a really, really wonderful talk. I really enjoyed it. And I was also wondering about the picture. And I agree that it makes you look like a mad scientist. Anyway, so for everybody who's still here, we do apologize if we did not get to your questions today, but we welcome you to follow up with us. You can send an email to webinars@aps.org, and we can forward your questions to Frank. And again, you should be able to find a recording to the archived video of today's webinar on the webinar page dedicated to this topic. Also, as you exit, please remember to complete the short survey. It's very helpful to us to get your feedback.
Unless you didn't like me. Don't do it. No, I'm kidding.
Frank won't see it.
Tell the truth. Tell the truth.
Okay. So this wraps up today's event, and we hope that you'll join us again next time. And I think we're going to stick around for just a few minutes. If there are any other questions, burning questions that any of you who are still here have, if you want to stick around and just type in some stuff, we'll stay around for a few minutes. All right, but thank you very much, everyone.
So, Frank, there was a question from the audience that we just never got to, and maybe more of a chat discussion is, what you and I could both somewhat talk about this is the question of developing countries and how is it that they could leapfrog the idea of the national grid and be able to, when looking at energy sources. So it's known well that there are many places that have avoided the landlines and telephones and gone straight to wireless. Is it something that can also be feasible, can be done when it comes to energy, for example?
Well, Peter, you know the Smithsonian place in Impala,
Yes.
To me, it's way off the grid. They get power there by having diesel generators, but they also have solar panels on the roof and batteries that try to store and so on. But in essence, if they really went through that place and with the right technologies that I think will come in the next few years, I think taking it fully off even the petroleum grid, if you will, and dispensing with their diesel generators for all but a day or two a year, I think is eminently possible. And I think that's an exciting possibility. And if they do that, why would you ever spend millions of dollars to run the power lines out to it, right? I mean, it would be, and the power that you could have locally and probably could be rather easily maintained and would be more economic and totally green. So I think there's lots of things that are out there for consideration that could make that possible. And so the way the power gets done in Africa, it's just not clear to me. It's not clear at all. And it may not be, there may not be time for Africa to go do it the Western way. They may get to do it their own way, and they may lead the rest of the world in showing what a post-carbon future looks like.
Well, I have to say I somewhat agree with you, having spent time doing research in Uganda and Kenya, and to see the whole power system and how it's done. Of course, in a lot of these countries, 90% are not connected to the national grid, and so it's been a big question: is how will this get done? And it seems like a lot of people are coming to the conclusion that the national grid will not be the answer to it.
Well, but as you're not connected to the national grid too, you get very careful about what the value of power is and how carefully you'll use it.
Exactly.
So I think there's whole social things that have to be put in place too. If you're a small village that's got a reasonable amount of power, if you have a few days without sunshine, for example, in very sunny parts of the earth, you might, there might even be social things that come into place where everybody goes, hey, we're going to turn, we're going to turn off more lights or do less until the sun comes back because we all got to share what we've got here.
Exactly.
And that just doesn't happen at all. What we think of as off the grid, there are many places that have a grid, but the grid is unreliable today.
Mm-hmm.
Look at Pakistan. Look at India.
Exactly.
There are brownouts every day in those major cities. And so, in essence, it's just not clear, how they break through some of those situations. A distributed, more socially responsible owned thing may work out very well and be again profitable for everybody that gets involved.
Exactly. And just another very late question that just came in, and which I think you might be able to give good advice in this is: do you have any particular advice on how to find a good partner to invest in something? Someone who, for example, complements your knowledge. You've talked about building up a team and the importance of a team, but do you have any specific advice, for example, when you
almost every major university today has a group that's focused on entrepreneurship. Mm-hmm. They don't tend to bring a lot of physicists into it, which is their mistake. But ideally, what they do bring into it are their B schools, their business schools, and their MBAs. And there are people getting MBAs today who don't want to go work for McKinsey, a big consulting firm, or don't want to go work for IBM or GE. They'd love to start a company. And they may have no idea what to do. They just may have good business sense. They like working with customers and doing sales and accounting and marketing and all those things. And so when you start a small company of 5, 6 people, it's often just one guy like the MBA, and it's 4 or 5, it's a couple physicists maybe and 2 or 3 engineers. And so, an early partner can be someone from a business school, someone from an MBA program. And often the entrepreneurship places at almost every major university that has a PhD physics program for sure has entrepreneurship programs as well. Get in touch with those folks. Or go to the MBA school. Find out what they know. Find out some guys there.
But they usually have good coffee and the Wall Street Journal for free.
Better coffee probably than the physics or astronomy department.
I used to do that a lot, so I speak that from experience.
Yeah, they got more money.
All right, Crystal.
Well, that's great, guys. So, I think we'll probably wrap it up here. But, again, Frank, thank you so much. This has been just a wonderful, delightful conversation.
Okay.
All right.
Great.
So, see you guys later.
Okay, thanks everybody.
Thanks a lot. Bye-bye.